Hello, welcome back. We get to start a new chapter, chapter 9. I'll put this up on the internet before I post the video. I haven't put the notes on there yet, so that'd probably be a good thing to do as well. The glossary as well. Chapter 9 is vocab heavy, especially 9.1, significance test, the basic. This is a vocab heavy section. Maybe the most vocab heavy. I'll write that. Most since our favorite section, 4.1. Well, since chapter 4 generally. So this is vocab heavy. So you need to know the words here. There's going to be a lot of vocabulary. There's going to be a fairly thick glossary. You all need to know it. You need to read this section. This is it's a hard section. This is one of the hardest. This is going to be on your test. This is in fact the last chapter, the last new idea that's going to be on your test, chapter 9, dealing with significance tests. And the question is, could it happen by chance? That is, we're going to be testing claims. And the way we're going to think about this is, how likely is a result this extreme or more extreme if, big if, the claim is true. So we're going to be asking, how likely is it to get a result like what we saw, that's that extreme or more extreme, if the claim is true? We're going to be assuming that the claim is true. This is going to be our assumption. In this chapter, we're going to assume that the claim is true, and we're going to say, okay, how likely was this? Suppose a basketball player claimed to be an 80% shooter. That's what they claimed. So we're going to say, okay, sure, they're an 80% shooter. I believe them. Who do we have in these classes that I could? Wasilla claims to be an 80% free throw shooter. She's not an 80% shooter, but she claims to be. Maybe she is. Maybe this is one of those skills. Maybe it's like Chloe with the Rubik's cubes. Maybe she's very good at this. I don't think so, though. And let's say Wasilla goes out and shoots 32 out of 50, and I say, "Oh, Wasilla, that's pretty good, 64%. I didn't think you could make 64%, but you said you were 80%. Okay." So you said you were 80%, and you went out and you shot 64%. So 64% is like our p hat, and 80% is like our p. I'm going to put a little naught there. That little naught, that's just like our claimed proportion. Claim. All right. So you claimed to be an 80% shooter. You went out and shot 64%. And let's say we simulated. This right here is a simulation of 400 sets of 50 shots. So this is a simulation of 400 trials. But this simulation is done assuming you're really an 80% shooter. So you went out. This is an assumption. This is a simulated. This is a simulation under the assumption that you're actually an 80% shooter, all right? And so the machine, this is like if we did Plinko, and you said, okay, put in p equals 0.8. Well, it's going to be 80%, but you're not going to get exactly 80% every time. There's going to be some spread. And what do we see here? Okay, 80%'s in the middle, and there's some spread. Okay, so we would assume that p hats would be distributed here normally with a mean of p naught, that is 0.8, and our standard deviation 0.8. 0.2 over 50. Those are formulas from the previous couple sections. We've seen those in chapter 7, dealing with sampling distributions of p hats. And we've also seen those formulas for p square root p naught, 1 minus p naught over n. We've seen those in the past couple chapters, dealing with confidence intervals and sampling distributions. Okay, and so remember, we said you're an 80% shooter. If you're really an 80% shoot, somewhere around 80% most of the time, within 1 or 2 standard deviations, and that would be, like these values in here, between 90 and 70%. Because, you're an 80% shooter, you're not going to shoot 80% every single time. There's going to be some variability, sampling variability, right? You don't do exactly what you say you're going to do every time. Not every poll gives the same value. Say 48% of people are going to vote for Donald J. Trump in November. Well, not every poll you take is going to give exactly 48%. There's going to be some spread around that. So what do we see? You shot 64%, and we say in the 400 sets of 50 shots, there were only 3 times when our shooter made as few as the observed 64%. So what's the idea here? The idea here is that 64% is a very rare value if they are really an 80% shooter. That is, you wouldn't get a value this often, very often, if you were really an 80% shooter. You'd get it something like, 3 out of 400 times. So that 3 out of 400, that's something that's going to happen about 0.0075 of the time. This is rare. This is rare. How rare is rare enough is the question that we're going to be asking soon. True or false, an outcome that would rarely happen if a claim were true is good evidence that the claim is not true. Yes, that is true. That is a true statement. But then the question is going to be how rare. But how rare is rare enough? How rare does something have to be before you say, I don't think that's right? 10% of the time? Is 10% of the time weird enough for you? Is 20% of the time weird enough for you? 1 out of 5, is that weird enough? Maybe 10%. 1 out of 10, is that weird enough? 5%. 1 out of 20, is that weird enough? 1%. 1 out of 100, is that rare enough? So it's going to depend. We're going to have to answer this question, how rare is rare enough? How rare is rare enough? Rare enough is going to be determined by our alpha level, our significance. All right, so we're going to have some hypotheses here, and normally this would be the part of the year where I shout about hos and has, but it's you can laugh about it, but it's not going to stick in your head as well. The statements being tested is called the null hypothesis, called the ho. Null hypothesis is usually assuming, what does null mean? No effect, no difference, no change from historical values. Null means nothing. Nothing interesting has happened. We don't have any evidence for anything. It is whatever they claimed it to be. The claim about the population that you're trying to find evidence for is the alternative. The alternative is some statement of an effect, a difference, or a change from historical values. So we're going to have hos and has, and we're always going to have to define these things because we're going to have some ho. Maybe the ho here was the proportion of times that you made your free throws was 80%. But I know Wasilla. And so I had a suspicion about Wasilla. I suspected that the true proportion was less than 80%. So that's what we're looking for here. That's what the example would have been with Wasilla shooting the free throws. Parameter versus statistic. Last little thing on this page. Parameter versus statistic. Your parameter, that's your true unknown value. And here, that's going to be, again, our P or our mu. Again, that comes from the population. Versus the known sample value. That'll either be a P hat or an X bar. So we're going to know, we know about the samples. We write hypotheses about the parameters. Write hypotheses about parameters. We don't need to make any hypotheses about the sample statistics because we can go find them. So again, these are the parameter and these are the statistics. All right, so we're testing claims about parameters by getting sample data, taking sample statistics, and saying how likely is this sample statistic, this 64%, if you're really an 80% shooter? Say it's not very likely. Okay, let's keep moving. What are you trying to show in your ha. So sometimes you're going to think, excuse me, that it's greater than the claim. The truth is greater than the claim. Sometimes you're going to think the truth is less than the claim. These two happen when you've got some prior knowledge. Prior knowledge. I have a sneaking suspicion about Wasilla, that she's not a great free throw shooter. Maybe she is. I don't know. I don't think she is, though. I don't think she is. So what are you trying to show in your ha? Greater than the claim. Okay, maybe you think it's better than that. So here, maybe our ho is proportion is equal to 0.8. Here, our ha might be the proportion is greater than 0.8. We think that they are better. Or maybe the ha is that P is less than 0.8. That is, that we think that they're worse. Maybe we don't know. Maybe we don't know. Maybe we don't know if Wasilla is better than 80% shooter. Maybe we don't know if she's less than 80% shooter. Maybe we don't have any idea. Maybe extreme values on either side would lead us to reject. Maybe we should go with a not equal to 0.8. That is, we just think that it's different. Here we don't have any prior knowledge. We're not sure if better or worse. We would take extreme values on either side. This is the better side. This is the worse side. This is the worse side. This is the better side. So sometimes we have some prior indication. We think, okay, maybe we think they're better than that, so we're just going to look for better than. Or maybe we think we're worse than that, so we're just going to look at the worse than that side. Or maybe we don't know. Maybe we just think it's different, and we're just looking, is it far enough away from the truth? All right, how to write your ho and your ha. You can only use parameters. That is things like p and mu, and they must be in context. The ho is always parameter equals the claim. The ha is going to be parameter is greater than, less than, or not equal to the claim. And that's your decision. And that decision right there, whether it's greater than, less than, or equal to, again, that's based on any prior knowledge we might have about the situation. All right. Sleep specialist believes that adults on the West Coast sleep less hours per day than adults on the East Coast. We take a sample, studies the amount of sleep West Coast and East Coast. What might the appropriate alternative hypothesis be? The appropriate alternative hypothesis is going to be based on that prior knowledge. That is, the amount of sleep for the West Coast is less than the average on the East Coast. That is answer option B down there. Try that again. Okay, there we go. All right, couple pages in. Good deal. You are going to have to slow this down and read this. This is just the hard section. There's a lot of vocab here, and we haven't even hit the hard vocab yet. For each of the following settings, describe the parameter of interest, state an appropriate hypothesis for a significance test. Okay, let's go ahead and do this. You could pause it. That'd be great. Pause. Okay, now we're back. We got somebody wondering whether some website tells us that 85% of teens are getting less than 8 hours of sleep. We got somebody asks whether this result holds. Is it still true? She asked a simple random sample of 100 students how much sleep they get. Great. 75 of the 100 said less than 8 hours. Great. So what is our P here? It's the proportion of students getting less than 8 hours of sleep. Our null hypothesis is that we're right, or that the natural proportion is correct. That is, it's 0.85. That is, it's not different from the US value. What's our ha? We don't know. Maybe it's not the same. We didn't have any prior knowledge. No prior knowledge. So not equal to. This 75 out of 100, that's not prior knowledge. That's after you did the study. So we don't get to take that into account. As part of the 2020 census, 10 minutes, 10 questions, that's all it takes. On average, this form will take about 10 minutes to complete. We suspect that the actual time it takes to complete the form may be longer than advertised. So mu might be the mean completion time for your 2020 census. Your HO, your null hypothesis, is that that mean equals 10 minutes, and our HA, our suspicion, is that that mean is actually greater than 10 minutes. What have we just done here? This is really secretly a state step. These are state steps for significance testing. The first thing we need to do is define what we're talking about, either the proportion of the mean of interest and the hypotheses dealing with those means. Great. Keep it going. On the back side, fun definition. The p-value. Everybody loves the p-value. The p-value of a test. Okay. What the heck is the p-value of a test? This is something you're going to need for an AP template. So why don't you go ahead and highlight the heck out of this thing, because it's a pretty darn important vocab word here. All right, so the p-value is the probability that we would get this sample result or one more extreme if the null hypothesis is true. How likely is it to get a result this funky or funkier? This far out or further out? Remember, like when we're talking about Wasilla shooting her free throws. She said she was 80% shooter, but then she went out and shot 64%. We said you wouldn't shoot 64% very often if you were really an 80% shooter. I think you're full of it. Maybe she just had a bad day. 80% shooters can have bad days. You don't shoot 80% every day. She's not a robot. But wouldn't be very common even if she was an 80% shooter. Be a very rare value. Okay, the smaller the p-value is, the stronger the evidence against the null hypothesis. Okay, so small p-values lead us to reject the claim. So what do we got here? We got a picture of a p-value. This is our observed p-value statistical significance. That's our significance threshold. You have the steps here for making this. Put the null hypothesis in the center. That could have been 80%. Put your statistic in the correct curve. That might be up here. Find the area as extreme or more extreme as your statistic. If it's two-tailed, it's both tails. If it's one-tailed, it's one tail only. I might have skipped over talking about tails on... Go back to this page here. These top two we called one-sided hypotheses. This bottom one we called a two-sided hypothesis. We were saying, okay, only evidence in one direction is going to lead us to reject here. Down here on the two-sided case, evidence in either extreme direction would lead us to reject. Okay. So we'll... Oh, good God. Confusing myself. All right, there we go. Good deal. Okay. So what do we have here? We have an AP template down at the bottom. State in context. If the true mean is the claimed value, the probability of finding a statistic in context as extreme or more extreme as your sample statistic mean is the p-value. So this down here is your AP template. How likely is it to see a result this extreme or more extreme? All right, what do we do? So we're going to find a p-value. That is, how likely is this result? I cannot overemphasize how important this thing is. The probability we would get a sample result or one more extreme. A result this far out. The conclusion, what do we do? We're going to have a statistical significance level. This is something like our rareness threshold. How rare does it have to be? If the p-value is as small or smaller than alpha, alpha looks like that, we say the data are statistically significant at the level alpha. Okay. What the heck does that mean? We're going to compare this p-value to alpha. If our p-value is less than alpha, we're going to reject the null hypothesis, reject the HO, and conclude the HA in context. What am I going to remember? Stupid little Snoop Dogg cartoon here. If the P is low, then the hoe must go. If you got a low p-value, that means your null hypothesis is in doubt. Low p-value puts the hoe in doubt. Okay, so you could also go with the Ryan Gosling, but I like the Snoop Dogg. We're never going to accept the hoe. We're either going to reject the hoe, or we're going to fail to reject the hoe. We either have evidence that says, this is suspicious, or we don't. We never accept the hoe. Think about this. How many times should Wasilla shoot free throws so we know she's an 80% shooter? What if she shot 5 and she made 4 of them? Say 80%, done? Or does she maybe have to keep shooting free throws forever to know she's really an 80% shooter? So we're never going to accept some claim. We're just going to say this claim is not very likely. Okay, so you're going to come back to Snoop Dogg when it's coming time to make decisions about rejecting or failing to reject the hoe. When it comes to conclusion statements, this is your conclusion statement right here. The do step is going to be to come up with our p-values. That's going to be the do step eventually. The conclude step is this. The only step we haven't talked about is the plan step. That's what we'll talk about tomorrow. Excuse me. All right, I'm back. Okay, so let's keep it going. If your p-value is too big, then you reject the ha and accept the ho. Never. Never accept the null hypothesis. Never do it. We're never going to accept it. We're never going to say this is true. We're only able to say with this stuff, this probably isn't true. The significance testing doesn't tell us what the truth is. It tells us what the truth probably isn't. And I know you don't love that. But that's what this step does. It doesn't find truth. It says that's probably not the truth. All right, for I need to rewrite this question, but we'll go with it. For a job satisfaction study, the hypotheses are mu equals 0, mu not equals 0. Data from the 18 workers gave x bar equals 17, sx equals 60. That is, the workers rated the self-paced environment compared to the machine-paced environment on average 17 points higher. So we didn't define what mu here is. Mu is the mean difference in satisfaction, self-paced minus machine-paced. And now is when I would put on the Drake and Josh video of them throwing sushi at the ceiling. Or the I Love Lucy video of them shoving chocolates in their hat. Or at the end of the hour, the Family Guy video of them putting pills in their mouth up until the end of the video, which is inappropriate. And I turned off then. But you've seen these machine versus self-paced environments. Think about somebody working on a conveyor belt. You know, are they happier working at their own pace or at the pace dictated by the machine? And yeah, whatever. Research performed the significance test and found a p-value of 0.2302. Explain what it means for the null hypothesis to be true in this setting. So A, if the null hypothesis is true, that would mean that on average, workers are just as happy to work either way. That is self or machine paced. On average, just as happy. Or there is no difference. No difference in satisfaction. On average. Part B, interpret the p-value in context. If the workers are truly equally satisfied, we would see a sample difference sample mean difference this large 23% of the time. Is 23% of the time rare? Does anybody think that's a rare thing? 1 out of 4? Probably not. Part C, this is a template one. Template. Since our p-value is greater than alpha, we fail to reject the hoe. We don't have sufficient evidence to say that the workers aren't equally happy with both methods. Okay. So we have a statement about our p-value compared to alpha, rejecting or failing to reject the hoe. We don't have enough evidence to say that the ha is true. Every time. Every time. So let's keep moving. You are going to need to pause this, write some of this down. You're going to have to go back and read it. My God, Liliana, you're going to have to go back and read things. Okay, so let's keep moving. Backside, I'm not going to do all these examples. I'm just going to do some of these examples. I might pause this one early. This one's going to get long. Yeah, I'm definitely not going to go this whole one. So you're going to stop here in a few minutes. What happy days. 2013, number 5. Oh, this is a fun one. Take 3 minutes. Just try and do this on your own. You're going to have to take a test over this stuff in like a month and a half. My God, that's how soon the AP test is. It's very soon. All right. Let's do it. Pause. Come back in 3 minutes. Pause. Did you pause? Okay, good. We did a little study on some meditators. 28 men live in a large retirement community. 11 said they meditated. 17 don't. We wanted to test whether their proportion of high blood pressures are different. We wanted to say, okay, think about this. If the proportion of meditators minus the proportion of non-meditators is 0, that means they have equal proportions of high blood pressure. Maybe the meditators have a smaller proportion of high blood pressure. If the study were to provide evidence against the hoe in favor of the ha, would it be reasonable for the psychologist to conclude that daily meditation, here's the key word here, causes a reduction in blood pressure? What do we have to say? Things about cause and effect. We need what? What do we need to make conclusions about cause and effect? What do we have to do to say that this thing causes that thing? 4.3? That 4.3 table. What do we need? Hopefully you've had enough time to think about it. If you don't, go back and look at chapter 4. We need random assignment. Whoop. N-M-E-N-T. Great. Random assignment to make conclusions about cause and effect. So it would not be appropriate because the men chose to meditate or not. There may be lurking variables associated with heart health. Great. And then 2009, number 5. I think we'll do this, and then I'll stop just to give you a nice 30-minute lecture. Because I could finish this. I'm not going to finish. No, it would take another 20 minutes, and I don't want to do that. So y'all are going to get 2 days to do your homework. But you better start it now, right? Because tomorrow's stuff is harder, and you're going to have more questions over it. Okay, so we're going to do this one, then we're going to stop, and you're going to be about ready to do half your homework for tonight. For many years, something about chest compressions versus MMR. However, some researchers believe that chest compressions alone to be more effective. Okay, we did a little study. 2 treatments are equal. CC alone produced a higher survival rate, and we got a p-value of 0.0761. Interpret this p-value, what this p-value measures in the context of the study. Well, let's talk about that. If the methods were the same in terms of survival rates, we would see a sample difference in rates this large or larger, 7.61% of the time. If the methods were the same, that is PMMR equals PCC, we would see a sample difference this large or larger, 7.61% of the time. Let's talk about what we're seeing here. We thought P1 minus P2, that 0 would be in the middle of it. We got a value out here. Area 0.0761. So here was our P1 hat minus P2 hat. It's way out here. And we said, okay, we would get a more extreme value than this, 7.61% of the time. Based on this p-value in the study design, what conclusions should be drawn? Use a significance level of alpha equals 0.5. So we were looking for something that happens rarer than 5% of the time. So we were looking for the rarest 5% outcomes. We weren't out there. So B, since our p-value is greater than alpha, we fail to reject the null hypothesis. We don't have evidence, sufficient evidence, to conclude that CC alone produces a higher survival rate. Since p-value is greater than alpha, we fail to reject the HO. We don't have sufficient evidence to conclude that CC alone produces a higher survival rate. Where am I getting that? CC alone that produces a higher survival rate. That is the HA. I have just stolen the phrasing of the HA and stuck it in the conclusion statement. And that's what you're going to do. I'm going to put a pin in it there because the second part of the stuff is hard. So this is part 1 of your 9.1 lecture. We'll talk about the types of error and power tomorrow. That's the hard stuff. You're about ready to do half your homework 9.1. I'd recommend you do that. There you go. See you tomorrow.